Gas behavior. In this lesson, we're going to look at how are pressure and temperature of a gas related. We'll look at how are volume and temperature of a gas related. In that section, we'll talk about Charles' law, and then we'll graph Charles' law. And then finally in this lesson, we will talk about how are pressure and volume of a gas related. And in that section, we'll talk about Boyle's law, and we'll graph Boyle's law. How are pressure and temperature of a gas related? So if you dropped a few grains of sand into your hand, you would hardly feel them. But what if you were caught in a sandstorm? The grains of sand would fly around very fast. They would probably sting if they hit you. Although gas particles are much smaller than sand grains, a sandstorm is a good model for gas behavior. So like grains of sand in a sandstorm, gas particles travel at very high speeds. The faster the gas particles move, the greater the force with which they collide with the walls of their container.
I told you, it's mud. Yes, that's right. It's raining mud. I'd say it's getting lighter. That's right.
particles move very similar to the way that sand would move in a sandstorm. The particles would move all over dependent upon the amount of energy that's supplied to them. Consider a gas in a closed, rigid container. If you heat the gas, its particles will move faster on average. So if you were to take a pop can and you were to put it on top of a stove and you were to heat it up, or maybe take the same can and throw it inside of a bonfire, the molecules of liquid would turn to a gas. The gas would then increase in pressure until the container could not hold in that pressure, and the container would more than likely explode. So those molecules are coming in contact with the walls of their container with a greater force as that pressure increases. The greater the force over the same area, that results in a greater pressure. When the temperature of a gas at constant volume is increased, the pressure of the gas increases. When the temperature is decreased, the pressure of the gas decreases. Perfect example of that, during a hot summer day, the temperature of the gases inside of a car tire, those gases increase in temperature. When they increase in temperature, the pressure also increases. As pressure increases, it puts strain on the interior walls of that tire, and you can have occur what you see inside this picture, where the increase in pressure actually causes a rupture in the tire. So if the pressure becomes greater than the tire can hold, the tire will actually burst. Looking at these two containers, they're both closed, rigid containers. The first one on the left-hand side has a low temperature. The one on the right, we're going to increase the heat temperature. So how would the change in pressure of the gas be shown in each pressure gauge? So we've got the pressure gauges. Temperature is here. With the lower temperature, there would be a lower pressure as well. If we were to increase the temperature, it would increase the pressure on the pressure gauge. How are the volume and temperature of a gas related? In the next slide, it'll talk about what happens to a balloon when it's slowly lowered into liquid nitrogen and we get it to nearly negative 200 degrees Celsius, and then we remove it. When the air inside warms up again, the volume is then increased again. The pressure remains more or less constant because the air inside of that container, the container being the balloon, the container itself is flexible. So the volume of a gas-filled balloon decreases as temperature increases, and then it increases as the temperature increases. So a gas-filled balloon at room temperature, which is about 20 degrees Celsius, we then put it into liquid nitrogen, which is negative 196 degrees Celsius. The balloon shrinks as the gas volume decreases. We then take the balloon out, put it on top of a counter where it warms. The balloon's gases then expand, and the balloon is eventually returned to its normal shape at room temperature. So let's look at this in action.
Frostbite Theater presents Cold Cuts, no baloney.
Just science.
Hi, I'm Joanna.
And I'm Steve.
And this is a container of liquid nitrogen.
And this is a really big balloon.
Let's see what happens when we place the balloon in the liquid nitrogen.
Okay. Whoa, wait. Isn't the balloon gonna pop?
We'll see.
Oh, man. Huh. Okay, so the balloon didn't pop. There's obviously a hole in the balloon somewhere because the air's leaking. So maybe instead of popping, maybe the balloon just got really cold and it cramped like an egg, and all the air is slowly leaking out of the crack.
Well, if that's the case, what's the balloon going to do when I take it out?
Nothing. It's a balloon with a hole in it, and all the air's gone.
Well, I'd say the air is still in the balloon.
So where's the air?
Right there.
That's water.
Nope. If that were water, it'd be frozen solid. That's liquid air. nitrogen, the air inside the balloon gets really cold. When particles of a gas get cold, they start to slow down and take up less space. If we can get the gas cold enough, we can change it from a gas to a liquid. That's what happened inside the balloon. We changed all the particles of nitrogen and oxygen to a liquid.
So how do I get my balloon back?
We just have to place it someplace hot, like the table.
Oh, so I get it. Now the reverse is happening. The heat from the table is making the liquid air inside boil. When a liquid boils and changes to a gas, the particles move faster. When the particles move faster, they take up more space, and the balloon gets bigger.
Exactly. Thanks for watching. I hope you'll join us again soon for another experiment.
Try that again.
Charles' law. French scientist Jacques Charles examined the relationship between the temperature and the volume of a gas that is kept at a constant pressure. He measured the volume of a gas at various temperatures in a container that could change volume. So a changeable volume allows the pressure to remain constant. So this is similar to what he used. The first container here has a low temperature added to it, and that same container, as that higher temperature is added to it, the volume could change. So the plunger would just simply go up. When the temperature of a gas at constant pressure is increased, its volume increases. When the temperature of a gas at constant pressure is decreased, its volume decreases. This principle is called Charles' law. So looking at Charles' law, and looking at a couple of different containers, how would the gas particles and piston look at the different higher temperatures? So we're starting out with a lower temperature, 20 degrees Celsius, approximately the same temperature that the room is. And we are adding heat to it and increasing the temperature to 200 degrees Celsius. And then continuing to add more and more heat to it up to 400 degrees Celsius. When we increase heat, the molecules want to expand. But remember, this container maintains the same pressure. So what ends up happening is the container, the plunger on it, ends up expanding. Same number of molecules, just more energy supplied to them. And as more heat is continued to be added to it, the plunger will continue to increase even higher. If we were to perform an experiment that tests Charles' law, we may look at the relationship between temperature and volume in a car's piston cylinders. So remember, we have the internal combustion engine inside of our cars. The internal combustion engine has a cylinder with pistons in it. At the end of the pistons, there is a small area where gasoline is added to the chamber. There is also a spark plug. When gasoline comes in contact with spark, it ignites. And that increases the area that the gas occupies. So the liquid turns into a gas, it occupies a larger volume, therefore moving the piston. So looking at this table, and the graph that is created from the table, we notice that each time the temperature increases by 20 degrees Celsius, the volume also increases. And specifically, the volume increases by 4 milliliters each time we increase by 20 degrees Celsius. Also make a note that we convert degrees Celsius to the degrees Kelvin for use in the graph. And in order to convert, we simply add 273 to the temperature in degrees Celsius. So we end up with a straight line, as you see here. As you can see in the graph, the data points form a straight line. Notice that the line passes through the point 0, 0. 0, 0 is called the origin. If we were to continue this line all the way down, it would pass through 0, 0. When a graph of two variables is a straight line passing through the origin, the variables are said to be directly proportional to each other. The graph of Charles' law shows that the volume of a gas is directly proportional to its Kelvin temperature at constant pressure. And we could even restate that by saying the graph of Charles' law shows that the volume of gas is directly proportional to its Celsius temperature at constant pressure. How are pressure and volume of a gas related? Suppose that you use a bicycle pump to inflate a tire. By pressing down on the plunger, you force the gas inside the pump through the rubber tube and out the end of the nozzle. The same thing happened with our rocket lab. We increased the pressure inside of the container, inside of the rocket. When we removed the pin, that pressure needed some place to go, so it rushed out the end of the bottle. What happens to the volume of air inside the pump cylinder as you push down on the plunger? What happens to the pressure? Both of these questions we're going to answer in the next couple of slides. But first, a little bit of background. Boyle's law. In the 1600s, the scientist Robert Boyle carried out an experiment to improve air pumps. He measured the pressure of gases at different volumes. Boyle's experiments showed that gas volume and pressure were related. When the pressure of a gas at constant temperature is increased, the volume of the gas decreases. When the pressure is decreased, the volume increases. This relationship between the pressure and the volume of gases is called Boyle's law. Boyle's law describes situations in which the volume of a gas is changed. The pressure then changes in the opposite way. So using a bike tire pump, when we press down on the plunger, we're going to take the gases that are inside of the plunger and we compress them into a smaller area. The volume decreases, but in this case the pressure is going to increase. For example, as you push down on the plunger of a bicycle pump, the volume of the air inside the pump cylinder gets smaller and the pressure inside the cylinder increases. The increase in pressure forces air into the tire. So looking at Boyle's law, he again used a cylinder that had a plunger that was movable. So what he did was he took weights and he added them to the top of the plunger. Looking at these pictures, we want to see which of these cylinders has the greatest pressure and the lowest pressure, and which cylinder has the greatest volume and the lowest volume. So let's rank the greatest as 1, and let's rank the lowest as 3. So let's start by looking at 1A, pressure. Does this have a greater pressure than the second picture or the third picture? Or does it have a lower pressure than the second picture and the third picture? It would have the lowest pressure. The molecules aren't in contact with the wall as often, therefore the pressure would be lower. 1B would be somewhere in between the two. And then 1C, the pressure would be the greatest. All of the molecules are confined into a smaller area. Volume, on the other hand, this picture would have the greatest volume. The second picture would have somewhere between the two, and the third picture would have the lowest volume. Takes up less space. So in an experiment, the volume of a gas was varied at constant temperature. The pressure of the gas was recorded after each 50 milliliter change in volume. So using this graph, you need to graph or plot volume on the horizontal axis, plot pressure on the vertical axis, and then also write a title for the graph at the top. Take a moment to do this on your own. The title of our graph is going to be Boyle's Law. I titled mine Boyle's Law graph. We are then going to plot the x-axis and the y-axis using the data points that are in the data table. So let's start right here. 300 milliliters and 20 kilopascals would be plotted over here. Let's jump down to the bottom of the chart. 50 milliliters and 120 kilopascals would be plotted up here at the top of the graph. And as we work our way through the graph, we would slowly plot out these points. Now notice our graph is not a straight line any longer. So looking at the graph of Boyle's Law, the one that we created, the manipulated or independent variable in this experiment is what? So the one thing that we changed in this experiment is the volume. The responding variable, or the dependent variable, the thing that was changed based on the independent variable, is pressure. So applying that, what happens to the pressure of a gas when the volume is decreased at a constant temperature? The pressure increases. So looking at the graph that we created, notice that the points lie on a curved and not straight line. The curve is steep at lower volumes, but it becomes less steep as volume increases. If you multiply the two variables at any point on the curve, you will find that the product does not change. So for example, if I take 300 milliliters and I multiply it by 20 kilopascals, I get 6,000 milliliters times kilopascals. Another example, 250 milliliters times 24 kilopascals. Again, it still equals the same product. When the product of two variables is constant, the variables are inversely proportional to one another. The graph for Boyle's Law shows that gas pressure is inversely proportional to volume at constant temperature. So we're staying at the same temperature. Pressure goes up, volume goes down. Volume goes up, pressure goes down. Inversely proportional.